In the practical, anything that's in here is fair game. Okay. I could ask you for the Schmidt-Lanterman. Yeah, these guys, yes. Okay. But it's more likely that they're going to, the majority of the questions will come out of the bolded yes. So, you know, if you're gunning for 100%, you need probably to read everything. If you're happy to have C+, B+, you know, the bold stuff only. And remember, be able to answer the questions. So at least if you go through this and make sure that all the questions that are there you can answer.
Oh, Schmidt-Lanterman. Okay.
So the Schmidt-Lanterman thing, clefts, are these guys here. See how we can see these clefts look like little funnels? There's one, here is another one, here is a part of one here, here is another one over here. All right, so you can see that they I think funnel-like is probably the best way to describe them. But now you compare those to this cleft here and to this cleft here. All right, so very clearly there is a difference between the two. The nodes of Ranvier tend to be this very straight, blunt node. Yes.
SCHMID.
It's in the yellow pages. Yeah, SCHMIDT. Lanterman. And a bit of trivia, my mother's maiden name was De Schmidt.
Bonus question. Yeah. I like that.
Yes.
Can you show the Schwann cell versus like actual myelin?
So remember that the myelin is actually the Schwann cell, because what a Schwann cell does to make myelin is it wraps its plasma membrane around the axon many, 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 many times. So the plasma membrane of the Schwann cell becomes the myelin. Okay, so there's not one part of it that is Schwann cell and one part of it that is myelin. The myelinated sheath is just this many, many layers of the plasma membrane of the Schwann cell wrapped around the axon fiber. Okay, so whenever you're looking at this and you see the blue here, you're looking at the myelin, but that is the myelin that is a Schwann cell. Okay. Now, if I ask you what is this dark blue structure, myelin would be a correct answer. Schwann cell would also be a correct answer. Okay. If you're not sure, you can put both. But again, I always put the caveat: if you're going to put more, make sure you don't contradict yourself and make your right answer wrong. Right, so below, so here, this long skinny nucleus is a fibroblast, yes. Here we have another fibroblast, long skinny nucleus. In fact, most of these long skinny nuclei that we see that are clearly sitting in the connective tissue are probably fibroblasts, okay? Normally what you can see, for example, this nucleus that we see here, even though it's almost out of the plane of section, that probably is a nucleus of that Schwann cell. All right up against the Schwann cell. But I'm more interested and concerned that you know that when we're looking at the sheath, that the white is the actual axon, that the blue around it is the myelin, and of course the myelin is from the plasma membrane of the Schwann cell. Another question, yes?
Can there be multiple Schwann cells per axon?
There can be multiple Schwann cells per axon, but not in the same place, okay? Because if you have an axon that goes all the way from your spinal cord to the tip of your big toe, you would imagine that you would have to have many Schwann cells along them, and and then where those two Schwann cells meet, that is your node of Ranvier, all right? Now, what you don't have in a myelinated nerve is multiple axons per Schwann cell. When you have multiple axons per Schwann cell, now you have an unmyelinated nerve. And remember, it is still a Schwann cell. It's considered a Schwann cell because it surrounds the axon. But when you've got this unmyelinated nerve, what happens is that the Schwann cells just put a single layer of their plasma membrane around each axon. So it doesn't wrap it continuously to make myelin. So Schwann cells in unmyelinated nerves means unmyelinated. There's not this multiple wrapping to make a myelin sheath. Okay? So unmyelinated nerves are associated with Schwann cells, but the Schwann cells don't make myelin. I beg your pardon? Okay, so if they're not making myelin, what they're doing is they're just wrapping just a single layer of their plasma membrane around the axons. It's obviously helping to keep all of the axons continuous, but it's also helping to make sure that those axons don't actually sit right next to each other. So that if you have, as your impulse is conducted along the nerve, that it's not jumping across axons. So it's keeping the axons segregated, but it doesn't have to wrap them in myelin. The myelin is actually ensuring that your conduction rate is faster, because when you have these myelinated axons, the impulses can actually jump from node to node. So it really can speed up the rate of conduction. I mean, that's why when you stick your finger into a flame, you can pull it out really fast, almost instinctively, because of that rapid rate of transmission. Your unmyelinated nerves don't have that rapid rate of transmission because they don't have nodes of Ranvier, right? And they don't have the myelin. Is that clear? Okay. All right. So we're done with the myelinated nerve. Let's go and have a quick look at the astrocytes. So when we look at this, we've got the section of neuroglia. And now what we're going to be looking for is we're going to be looking for cells that have lots and lots of processes coming off of them. In fact, let me see if I can get, here we are. So lots of cytoplasmic processes, and those cytoplasmic processes are all going to be directed towards small capillaries that are sitting within the neuroglia. So in this case, here we have good examples of those neuroglia cells. One here, one here, one here for the astrocytes. And in many places we can see their processes, but we can't actually see the cell body at all. And then lastly, we'll go see the ganglia. And again, now the ganglion is not in the central nervous system. The ganglion's outside the central nervous system, but it does have neuron cell bodies in it. So it's basically these clumps of neuron cell bodies that you can see. So remember, neurons are very large cells. So what you're looking for is you're looking for an extremely large cell relative to the size of all of the other cells. So here we can see we've got lots and lots of other small cells, very large cells, nice clear nucleus, and nucleolus in the center. Now, aside from the slightly different appearance to the surrounding tissue, one of the ways that you know that you're sitting in a ganglion, when you take this up to a higher power, is when you look at these neurons, you'll see that they have these other nuclei closely associated with them. And it looks like the nuclei are almost embedded in the plasma membrane, but they are separate cells, but they sit very close to the neuron cell body, and these are called satellite cells. So when you see a neuron cell body with these satellite cells around them, then you know that you're looking at a ganglion outside the central nervous system, not in the central nervous system. And remember, because you have ganglia and neuron cell bodies here. These neuron cell bodies will have processes coming off them, and those processes are axons, and